Hi everyone. So this is going to be our final lesson on quadratic functions, and this example is going to be on optimization problems. So you'll see I have here in a dramatic rectangle, and it says optimization problems, aka word problems involving the vertex of a quadratic function. And underneath here, I'm going to write the following. The idea behind this is if a situation, a scenario, can be modeled by a quadratic function, we can figure out the value of the input, so I'll just say of x, it's not always x, but I'll just say x, at which the optimal result is achieved. For our purposes, the optimal result is often the maximal possible value. But you can imagine a situation where it can be the minimal possible value. So again, for our purposes, it'll almost always be the max, but it can be the min too. It's just not something we see a lot of. On the next 2 pages, I am going to work through 2 examples with you. Both of them are examples from your homework. So I highly recommend that you watch the rest of this lesson very, very carefully. And at the end of the second example, I'll just kind of make an overarching statement to complete this conversation. So here's the first example. When a certain drug is taken orally, the concentration of the drug in the patient's bloodstream after t minutes is given by C of t equals 0.06 t minus 0.002 t squared, where t is between 0 and 240 and the concentration is measured in milligrams per liter. When is the maximum serum concentration reached, and what is the maximum concentration? So the first thing that I would like to do is I would like to graph a really basic graph here. So first of all, notice we are told that we're only looking at time between 0 and 240 minutes, right? So our patient takes this drug, and we're looking at the concentration of the drug in their bloodstream for 4 hours. So in this function, the input is the time since the patient took the drug. So we start at 0 and we end at 240. So I'm going to put 240 here, 8 squares later, because why not? The outputs here are the concentration of the drug in the patient's system. Now, if you think about this, having probably taken like a Tylenol for a headache in your life, or, an Advil for something, you all know that when you first take it, your headache doesn't go away. That's because the drug hasn't entered your bloodstream. And then eventually it enters your bloodstream, and then at some point it reaches its peak concentration because your body starts to break it down, your body starts to metabolize it. Different organs metabolize different substances. So it might be your liver, it might be your pancreas, whatever. And after that peak happens, the concentration of the drug in the system starts to go down until eventually your kidneys go to work and you're able to expel it from your body, right? So here, let's just see really quickly, because I want us to have a pretty good picture. So not surprisingly, C of 0 is 0. If you plug 0 in for t, you'll get 0. not surprisingly, when the patient just takes the drug, there is no detectable drug in the patient's system. And then C of 240, which is the time at which we stop monitoring the patient, is 0.06 times 240 minus 0.0002 times 240 squared. So I'm actually going to go ahead and very quickly punch this into my calculator here. So we have 0.06 times 240, which is 14.4, minus 0.0002 times 240, which is 11.52. So four hours after the patient took the drug, the concentration of it in their bloodstream is 2.88 milligrams per liter. So what we're going to see here, because this is a quadratic function, is we're going to see a parabolic shape. Notice that the leading coefficient, which is the t-squared coefficient, is negative, which means our parabola is going to be opening downward. So it's going to look something like this. I'm going to totally fudge this. I'm not going to worry too much about the specifics. So it's going to go up, 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 up. Somewhere it's going to peak. And then 4 hours later, it's down to 2.88 milligrams per liter. So that's when we stop monitoring our patient. There is our vertex. So this value is the time at which the max concentration is reached. And then this, the kind of second coordinate, the y coordinate if you want, the c coordinate in this particular example is the maximal concentration. So even though this is a problem about drug concentrations and patients and whatever you have, at the end of the day, the situation, the concentration of the drug in the patient's system is modeled by a quadratic function, so we can use our knowledge of quadratic functions to answer the question about max concentration. So from the last lesson, if you want, you could use, the whole completing the square process here. And I actually have students every semester who choose to go through that process. It makes it feel more familiar to them. And if you want to, that's fine. But because the coefficients are kind of cumbersome, there's a lot of decimals, and it might be easy to lose something along the way, we'll just use, for the purposes of this example, that the vertex occurs at negative b over 2a. Now, mind you, there will absolutely be situations where I give you a quadratic function and I specifically ask you to show me the process of putting the function into vertex form using completing the square. I do expect that you're able to do that. I will be testing you on it. But when the function is messy, has big gross coefficients like this, it's fine to just use the sort of shortcut that we found in the last lesson. Okay, so let's label here. So here B is 0.06, A is negative 0.002. So negative B over 2A is negative 0.06 divided by negative 0.0004. So notice that they're both negative. That makes us feel good because time should be positive. So it makes us feel good that the value we're getting here is in fact greater than 0. So 150. So what we just found here, kind of going back to our picture, is that 150 minutes after the patient takes the drug is when it reaches maximum concentration in their system. So for example, if this is a Tylenol-like substance, 150 minutes in is when the patient can expect to see maximum relief of their symptoms. So Tylenol relieves things like fever, aches and pains. So about 2.5 hours after you take it is when the blood is maximal. This might also be useful in conversations about like dosage, right? So it might be very important that you not take this drug, within 2.5 hours of when you first take it. Because within that first 2.5 hours, the concentration of it is still growing in your bloodstream. So if you add more, you could be putting yourself potentially in grave danger of having too much of it in your system at one time. So that is the time at which max concentration is reached. To find max concentration, which is the other part of the problem, so to find maximum concentration, you could go back to our last example where we were able to kind of find a shortcut for the y-coordinate of the vertex. But as I told you before, it's much clunkier and usually we don't really bother remembering it. We just want to know what is the value of the concentration when t is 150. So we're just going to find the output that this function assigns to the input 150 by plugging 150 in for t. So we have 0.06 times 150 minus 0.0002 times 150 squared. So let's punch that in here very quickly. So we have 0.06 times 150, which is 9, minus 0.0002 times 150 squared, which is 4.5. So the maximal concentration that the drug reaches in our system, if this is the concentration function, is 4.5 milligrams per liter. So again, knowing the concentration, this may also be a part of the conversation about dosage. So maybe we're going to determine, hey, is this concentration dangerously high? Is it dangerously low? In which case, if it's dangerously high, well then we need to lower the dosage. If it's too low to achieve the relief that we want the drug to provide or to achieve whatever effect the drug is supposed to have, then we need to up the dosage. So this kind of conversation is actually a conversation that happens quite frequently in the pharmaceutical landscape. Before I move on to the next problem, I want to point out to you that in this example, you were given the function that we were trying to optimize. So we didn't have to create it ourselves. Sometimes that'll be the case. Other times you'll have to create the function yourself. Case in point, this problem. So I like this problem a lot myself, but it sometimes presents a little bit of a challenge to students, so I like to do it with my students. So a rain gutter is formed by bending up the sides of a 30-inch wide rectangular metal sheet as shown in the figure. So imagine you started out with this rectangular sheet, and then you took the sides of it and you bent them up like so. So you ended up with this sort of shape, right? So you took the sides of your metal sheet and you bent them up. And what I hope you all can see is that it's labeling for you that how much you bent up is up to you. So you could take just a little bit and bend it up. You could take a lot and bend it up. That's your call. So the first thing that we're going to do in this problem, this is a multi-step problem, is we're going to find the function that models cross-sectional area in terms of x. Then we're going to find the value of x that maximizes that cross-sectional area. And finally, we're going to find what is that maximum cross-sectional area. So what is this cross-sectional area business they're talking about? It is this area here. So I'm outlining the cross-section of this gutter. It is that rectangle. So what we want to do is we want to express this area in terms of x. Well, let's call it a of x to be boring. So again, x is the amount that we bent up on the sides, and a is the area of the cross section. Okay, so this is x. Now, in order to achieve this rectangle, we had to bend x up on both sides. So that means this here is also x. Now remember, we started with 30 inches total. If we took 30 inches and then bent x up on both sides, what's left over? So this piece here, what is that piece or this piece? They're the same length. Well, it's 30, which is what you started with. Take away 2x, because those 2x's got bent up on the sides. So it's a rectangle. The area of a rectangle is length times width. So the length and the width are x, and 30 minus 2x. So as it's actually going to turn out, the area function here is quite a bit simpler than the concentration function that we had in the previous example, but we had to find it ourselves. Okay, so 30x minus 2x squared. That is the cross-sectional area. Once again, I want to draw you a picture. You have known me long enough at this point to know that anytime I can, I draw you pictures. So here, we once again have a situation where the value of x cannot be negative. You can't fold up a negative number of feet or inches. That has to be a non-negative number. If you fold up nothing at all, you have a flat sheet of steel. So there is no area at all, right? And by that same token, if x is 15, right, that's half of 30. If you fold up 15 inches on either side, you're just closing it up like a book, and then you have no area that way either. So when x is 15, you are back to having no area at all. So our parabola looks something like this. Notice once again, the leading coefficient is negative. So that means our parabola opens down. It looks something like this. And then it comes back down. So the question is, where does this happen? Right? So here is the amount to be folded, amount to fold. And then here is the maximum cross-sectional area. Now, some of you might be thinking, hey, wait a minute. In this instance, I know both of my x-intercepts, and I know that the line through the vertex is the axis of symmetry. So shouldn't the vertex happen right smack dab in the middle between the two x-intercepts? If you're thinking that, you would be right. But since we haven't talked a lot about that, let's go ahead and work it through, and then we'll kind of circle back and make sure that we're all there at the same time. So we want the vertex of this quadratic function. So I'm just going to say the vertex of a of x, which is a quadratic function. So again, you could do the whole completing the square. You could use completing square. And again, I encourage you to do it if that's what feels right to you. But since we have it, and to save time, in fact, I'm going to write that. To save time, we'll use the negative b over 2a. Okay? Because we worked that through. We know why the vertex occurs at negative b over 2a. So we can just go ahead and use it. Looking back at our function, b is 30, a is negative 2. So remember, b is the x coefficient, a is the x squared coefficient. So negative b is negative 30. 2a is negative 4. That's 30 over 4. Oh, hey, that is 7.5. Or 15 over 2. Let me erase it so it looks a little neater. So those of you who were thinking, shouldn't it just happen halfway between the two x-intercepts? You were absolutely right, and that's because of the symmetry of a quadratic function. So when we fold up, um, 7.5 inches on both sides, we achieve maximal cross-sectional area of, so now let's find the maximal cross-sectional area. So remember, the area is 30x minus 2x squared. So to find the area at 7.5, we're just going to plug it in to a of x. So we have 30x, 30 times 15 halves, minus 2 times 15 halves squared. So what's nice here is that the 30 and the 2 will reduce, so we'll just have 15 times 15 here, which is 225, minus, so 15 over 2 squared is 225 over 4, multiply it by 2, you get 225 over 2. And you can do this all in decimals if you like, that's fine by me. But I actually kind of like doing it with fractions. So this is our area, which if we wrote it as a decimal or a mixed fraction, this is 112.5 square inches. The last thing that I will say to you here is when you have word problems, pay attention to your units. So in this case, the maximal area is in inches squared, and the amount that we folded up is in inches. In the last example, the time was in minutes, and the concentration was in milligrams per liter. So especially when you encounter problems like this on tests and quizzes, I'm going to be clearly asking you, state your final answer with all appropriate units when we're doing problems like this. So this is our final lesson on quadratic functions. It's the lesson on optimization. You'll notice that you have a few optimization problems in your homework on quadratic functions. I anticipate that those are going to be a little bit of a challenge, so do not hesitate to post about them in the discussion forums. I will be monitoring those closely. Do not hesitate to message me and Arena about any questions that you have, and we will be happy to help. And make sure to leave yourself plenty of time to work on that homework assignment. Especially the last few problems are probably going to take you a little bit of thinking about. That's all that I have for you this week. Have a good night. Bye.